Greetings and welcome to this lecture. We are in module 2, which is two-terminal MOS structure. In this video, we will discuss about what is the impact of gate body voltage when you connect across the MOS capacitor. We will see the different conditions of operation of MOS capacitor, meaning you have a MOS capacitor like this, a metal plate, an oxide and a semiconductor. Across this metal oxide semiconductor structure, you are applying a voltage VGB, which is gate to body. So this VGB can be positive, it can be negative, or it can be exactly equals to flat band condition. So we can have different region of operation which can be classified as flat band, accumulation, depletion, or inversion. So we will see what is the condition in terms of energy band diagram point of view. Then we will calculate or we will model what is the carrier concentration in the channel, which is QC dash, is can be given in terms of applied potential or in terms of surface potential, psi s. These are the learning outcomes of this lecture, which gives you the idea of the applied gate voltage influence on the surface potential and carrier concentration. Let us do a quick recap. In the last lecture, we have seen that not only the contact potential between gate and body is responsible to cause a charge pileup into the semiconductor, rather the presence of charge in the oxide layer, which is Q naught dash, is also causing a charge pileup into the semiconductor, and hence if we want to remove the charge from the semiconductor, we need to connect a battery in such a way that the charges is not piling up into the semiconductor. This is referred as flat band voltage. So the flat band voltage is nothing but the difference between phi ms minus Q naught by Cox dash, where we are taking Q naught dash and Cox dash, which shows that charge per unit area and oxide gate oxide per unit area respectively. We have also seen what is the potential and charge balance equation in two terminal MOS cap structure. When we applied the VGB, this VGB is actually dropping or potential drop across the oxide, which is this layer psi ox, the potential drop across the surface, which is actually causing the charge pileup here. This charge is refers to as channel charge, and there is a potential drop across these two contacts, which is contact potential. So we have seen that the potential balance equation can be written as VGB is equals to psi ox plus psi s plus phi ms. We have also seen what will be the change in gate voltage. So the change in gate voltage is nothing but reflect across the change in oxide potential and the change in surface potential. For example, you can see here you are applying a potential which is nothing but VGB. This VGB is constant throughout the metal, considering this is an equipotential surface. Now the potential will drop across the oxide, the potential will drop across the surface, and this is just constant, which is nothing but a contact potential. Here as of now, we do not know what kind of behavior this is, whether it is exponential, linear, or what, right. We will see in subsequent slide, but there will be a contact potential, there will be a drop across the oxide and across the semiconductor, referred to as psi ox and psi s respectively. Following the same, we have written the charge balance equation, which can be considered as Qg dash plus Q naught dash plus Qc dash is equals to 0, where Qg dash is gate charge per unit area, Q naught dash is an oxide charge per unit area, and Qc dash is a resultant channel charge per unit area. We have also seen that if you change the VGB or you tune it, then what will happen? The change in gate charge is exactly equals with an opposite side of the channel charge. Let us do a brainstorming before moving further. So we have a question related to a flat band voltage, which says that consider a MOS structure for which the flat band voltage and the oxide thickness are linearly related. So we have a graph given between the flat band voltage, which is V flat band voltage, and Tox. Tox here is refers to as oxide thickness. Consider the gate electrode is N plus polysilicon. So, we have a layered structure like this. This is an oxide and this is a semiconductor. In the initial lectures, I have told you that it is not mandatory that the gate metal is made up of metal only. Here it is given that the gate metal is made up of polysilicon. So, this is N plus poly. N plus stands for highly doped. So, this is polysilicon gate. The effective density of states is given that Nc equals to Nv equals to 10 to the power of 19 per centimeter cube. We need to calculate what is the substrate doping. Considering this is substrate, at this stage we do not know the type of the substrate. So, this is substrate. Now, the first is we need to calculate what is the work function of N plus poly gate. So, if you remember the definition of work function says that the minimum energy required to remove the electron from its Fermi level in the semiconductor to the reference level. So, this is let us say reference level and this is Fermi level, which is EF. So, I am making the band diagram only for semiconductor, which is nothing but N plus polysilicon. Here, as we know, this is N plus means degenerate semiconductor. If it is degenerate semiconductor, the Fermi level is exactly aligned with the conduction band. So, the Fermi level and conduction band are at same level, and we know that the difference between conduction band and the reference level is given by electron affinity. So, here the phi m poly or the work function of the poly gate is nothing but equals to chi. If it is a p-type semiconductor or if it is a p-type poly, then ultimately it will given by chi plus Eg. Here this is the known value for silicon, which is 4.05 electron volt. Now, we have given the value of flat band voltage versus Tox. If Tox is equals to 0, it means the flat band voltage value is what? Minus of 0.15. If we go through the equation, V flat band voltage is equals to phi poly minus phi of substrate or substrate minus Q naught divided by COX prime. This COX prime can be written as phi poly minus phi substrate minus Q naught prime divided by epsilon OX prime into Tox. If Tox is equals to 0, you will get what? Flat band voltage value is given from this graph. So, V flat band voltage is equals to phi poly minus phi of substrate. So, this is given as minus 0.15 is equals to phi poly we have just calculated, which is nothing but what? 4.05 electron volt minus of phi s. So, phi of s here stands for substrate or semiconductor is actually 4.05 plus 0.15, which is nothing but 4.20 electron volts if it is Q times of phi substrate. Now, if I will go back, that phi substrate is nothing but for N type semiconductor, this is my reference level and this is chi, and I need to measure the Fermi work function from the Fermi level. So, this is EC and the Fermi level is just here, because this total quantity what we got is phi s, which is nothing but 4.2 electron volts. So, this quantity between EC to EF is nothing but 0.15. Now, if we got the difference between the conduction band and the Fermi level, then by using as basic equations we can calculate what is the doping of the body. So, we can get N D, because it shows that number of electron concentration into the N type semiconductor, because the Fermi level is close to conduction band. So, it can be written as Nc exponential of Ec minus of Ef divided by Kt. You have the value of Ec minus Ef, we can get, and we have the value of Nc also, which is effective density of state. So, it is given as 10 to the power of 19 exponential of 0.15 divided by this Kt over Q is a thermal voltage, or Kt is a thermal energy, which is 0.02586, or you can consider as 26 millielectron volt. Then the final answer is around 10 to the power of 17 per centimeter cube. So, we can conclude that the body of this structure with which we started our analysis is made up of N-type semiconductor having a doping of 10 to the power of 17 per centimeter cube. This is polygate. There is another thing we need to calculate, which is what? Oxide charge. If you see, the slope of this curve is also a helpful thing, in the sense, if we write Q is equals to Cv, again Q here is can be oxide charge per unit area, right. So, Q naught dash can be given as the slope of this line, right. It can be written as Q naught is equals to C. C is can be written as epsilon ox divided by T ox, and this V is nothing but what? V flat band voltage. So, ultimately you are calculating a slope delta V flat band voltage divided by delta T ox, right. So, ultimately you can rewrite as minus of epsilon Ox, which is relative permittivity value epsilon naught into epsilon of SiO2 into flat band voltage. So, if you take a slope of this between these 2 points, you can simply get the slope of this line, right. So, the slope of this line can be written as minus of 0.3 minus of 0.15 divided by 30 nanometers minus 0. So, ultimately these values, if you put all the values, so relative permittivity is 8.854 into 10 to the power of minus 14 farad per centimeter. Epsilon SiO2 is 3.9, this will give you 0.15 divided by 30 nanometers. Again, you have taken the, you have to take care about the units. So, here you need to take what? In centimeters, minus 7 centimeters. When you calculate this, the overall value is coming out to be 1.7 into 10 to the power of minus 8 coulomb per centimeter square. Do take care about the units, because here the unit is coulomb per centimeter square. You are talking about the oxide present in the silicon dioxide interface. It is a radial charge, it is not a bulk charge. So, if it is a radial charge, ultimately you cut down one dimension, and hence the unit is will be per centimeter square, not per centimeter cube, like you have a unit of donor density and all, right. Okay. Let us move further and see what will happen if we apply the voltage VGB between gate and body terminal of a MOS capacitor, and then what is the implication of this gate to body voltage into the bands of the semiconductor. We all know that the p-type semiconductor is can be given by EC here, EV here, the Fermi level is close to the valence band, and this is an intrinsic Fermi level, right. So, throughout this analysis we are considering that our body is made up of p-type semiconductor, right. This is a picture of a flat band condition, which says that when you apply a voltage exactly equals to flat band voltage, which is nothing but what? Phi ms minus Q naught divided by Cox dash, right. So, if you apply the same amount of voltage from the external battery, the bands are flat. If there is bands are flat, or physically we have discussed that in the flat band condition there is no charge into the semiconductor, and hence the channel charge Qc dash is nothing but 0. If there is no charge, if there is no bending into the bends, ultimately what is the surface potential? The surface potential is the potential which measured from the surface to deep into the body, right. So, this is a surface potential which is also 0, because there is no bending, but there will be a bending into the oxide, because you are connecting a negative supply or the overall supply as V flat phi ms minus Q naught divided by C ox dash. To maintain this, if you are connecting a negative here, this potential energy will increase, right, and hence this bending will be look like this. So there will be a bending into the oxide, but there is no bending into the surface. We are much more concerned about what surface potential is and what are the charges present into the semiconductor. So what will happen if we apply a voltage which is less than flat band voltage? It means you are applying a negative voltage into the system. If you apply a negative voltage, so the negative charge will come into the metal plate, right? These negative charge requires a positive charge at the opposite plate, which is nothing but what? A semiconductor. So from where the positive charge will come up in the p-type body? Obviously, if it is a p-type semiconductor, the holes which are majority here will ultimately get attractive force toward the surface, and hence all the holes will get accumulated near the surface. If the holes are actually accumulating near the surface, this region is called accumulation region. Now again, use a general analogy or general sense to rewrite these equations. What I said is, we are applying a negative voltage or the voltage which is less than flat band voltage. It means here you are applying a negative voltage. If there is a negative voltage, the bending will be more, right? Because again we know that the potential energy of an electron is representing opposite to the potential, right? So it is above, this is below, which says that this is negative voltage and this is positive voltage. Now what is the channel charge? Yes, we have argued here the channel charge is nothing but what? Positive. If it is positive, you can think like that, a semiconductor is there which is p-type semiconductor, you are becoming more p-type. If you become more p-type, it becomes positive. If it becomes more p-type means what? The valence band is going closer to the Fermi level. So here in the system under equilibrium, the Fermi level is aligned and the valence band near the surface is going closer to the Fermi level. So the bending will be upward. Again, we all know that EC and EI follows the same trend which what EV is following. So ultimately the bending will be upward. If the bending will be upward, again following the same thing, how we can relate the potential and potential energy. If this is upward and this is downward, means what? This is negative and this is positive. If this is negative and positive, meaning the surface potential is what? Negative. You can simply use a common analogy or common understanding, like if you are applying a negative voltage, ultimately that negative voltage is responsible to cause a positive charge into the surface, and hence the bending will be upward. So the surface potential will be negative into the accumulation, correct? Now what will happen if we apply a positive voltage? This is of much more interested part of our MOS structure or MOSFET. When we are dealing about the enhancement MOSFET, obviously we will discuss about that depletion and enhancement MOSFET in detail. So what will happen? You apply a positive voltage. When you apply a positive voltage or the voltage greater than V flat band voltage, so you can think like that, you have a plate of capacitor over which from the top you are actually applying a positive voltage. Then this positive charge will come up. If the positive charge will come up, exact amount of negative charge should come up in the semiconductor surface. So let us consider you applied a VGB. So I am taking here a layman numbers, some layman values, VGB of 1 volt. If VGB of 1 volt is applied, what will happen? It will give you 100 positive carriers at the metal plate. That 100 carriers requires a 100 negative carrier into the semiconductor. So what it will do? In a very preliminary stage, it will repel the holes back to the body. So ultimately the holes from the surface, it will go to the body. If the holes will leave from the surface to the body, ultimately what will happen? There is uncovered immobile ions come into the picture. That is what is called depletion region. In p-n junction theory, we have already discussed that part, depletion region, right? And your 100 positive ions from the surface is actually satisfied with the 100 negative ion into the surface. That is called depletion region. In depletion region, if I go and write the charge condition and the potential condition, you see the charges in the semiconductor is given by negative or acceptor ions, right? So this acceptor ions is negative and hence the total channel charge is what? Negative. If the channel charge is negative, means what potential is responsible to cause a negative charge? It's positive. So surface potential will be what? Positive. If you see a band diagram, and this is much more interesting, and please pay attention here about what the quantities we are using to plot the band diagram, right. So this is the band diagram of a p-type body deep in the bulk. So we are talking about here, deep in the bulk, we are not talking about the surface as of now. Deep in the bulk, it is clear that if it is a p-type body, you have a Fermi level, you have a valence band which is close to the Fermi level, there is an intrinsic level, and there is conduction band. Now what will happen when you apply a positive voltage at the outer terminal? If you apply a positive voltage, then what will happen? The charges will become negative at the semiconductor. If it becomes negative, means what? It's like you have a p-type semiconductor and it becomes more negative. If it becomes more negative, means what? You are actually taking hole out of it. If you are taking a hole out of it, becomes less p-type. If it becomes less p-type, the valence band will go away from the Fermi level, and hence the bending will be downward. Similarly, the EI will also bend downward, and similarly here it is downward. So the bending will be downward. What will happen if exactly EI touches to EF? What is the difference between EI and EF? We know that EI minus EF divided by Q is nothing but KT over Q log of Na by Ni. We call this as a Fermi potential phi f. So exactly if EI touches to EF, ultimately the semiconductor is nothing but what? Intrinsic semiconductor. So this depletion case, the bending will be downward, the total potential, surface potential will be positive. You can think like that also, like a positive potential causes a negative charge, right. So here this is positive voltage, so the surface potential will be positive. You can also get a bending into the oxide because you are applying a positive voltage here. So this edge or this end will be downward, this end will be upward. This voltage drop is nothing but what? Oxide drop. Now what will happen if you increase or if you tune the VGB from 1 volt to, let us say, 2 volts? It will add another 100 positive ions. So earlier it was 100, another 100 positive charges into metal plate. Now you cannot increase the depletion region further. So what will happen? It will pull the electrons which are in minority, which are minority carriers in p-type semiconductor. They are getting pulling force, right? They are getting a attraction force towards the surface, and hence there will be a charges coming into picture, which is nothing but electrons. That is what we called as inversion. So if you increase VGB beyond a certain limit, what will happen? These positive charges causes a negative charge to come up from the deep in bulk body, which is p-type. So the electrons will come near the surface. It is like that. You take an analogy. Suppose you want to dig a pit into the surface. So what will happen? You will shovel the soil, right? So when the moment you are shoveling the soil, ultimately the soil is removed from the surface. That is called depletion region. So you go on increase shoveling, right? So ultimately you are putting the soil back to the from the dig, right, or from that pit. So what will happen? This is called a depletion region. But can you go on digging that particular surface? The answer ideally yes, you can go on decreases, right, decrease that height, or you can remove the soil and all. But practically if you see, the moment you go on decreasing, right, or you go on pitting that, you consider this condition as an inversion. It means if we increase the positive charge here, then what will happen? There will be a negative charge come into picture, right. These negative charge now can be given by immobile ions and the inversion charge or the electrons. In this condition, the electrons are coming from the body, which is nothing but the minority carriers of p-type body. So what is happening in the band diagram? If you are increasing a positive voltage here, the bending will be more steeper, and that is nothing but psi-ox, as we have discussed. Now what will happen here? Here you see what we generally say in the p-type semiconductor, the Fermi level is near to valence band, right, and in in n-type semiconductor the Fermi level is near to what? Conduction band. So, if we see this picture, here the dotted line is the intrinsic level, this is Fermi level. So, Fermi level is below the intrinsic level and hence this is what? P-type semiconductor. But what is happening if you increase the voltage? If you increase the voltage, your surface potential is increasing. If surface potential increasing, the bending will be more. If the bending will be more, near the surface you see, this EI is going below the Fermi level and hence this is actually showing you that this surface is no longer suitable or no longer reflecting the p-type semiconductor, rather it shows as an n-type semiconductor. So, if the Fermi level goes above the intrinsic level, then this becomes what? N-type semiconductor. This condition is suitable for n-type. So, what you did? You applied a voltage, a positive voltage in the p-type body. By this capacitive action, you actually attracted so many electrons such that the surfaces get inverted. That is what is called inversion. So, in inversion what will happen? Your surface potential is positive, your channel charge is negative, and here the channel charge is actually governed by the depletion charge as well as the inversion charge. Now, we will see how to calculate or how to model this channel charge with respect to the surface potential. To do that, before going into the equation, let me revisit into the basics of band diagram. I am drawing a band diagram for a p-type semiconductor. If it is a p-type semiconductor, this is an intrinsic level EI, this is conduction level, conduction band, and this is valence band. The Fermi level is somewhat here, close to valence band. This quantity we call it as what? Phi f, a Fermi potential. Now, I want to write the equation for hole concentration and electron concentration into the p-type semiconductor. So, in a p-type semiconductor, the hole concentration can be represented by what? P naught under equilibrium, and electron concentration can be represented by N naught. So, again we will use a general common sense, like P naught in a p-type semiconductor is higher than what? Intrinsic carrier concentration. So, intrinsic carrier concentration is Ni. We need to have some positive exponent which makes P naught greater than Ni, and hence instead of by hearting the equation, we can just use this thing to calculate what is the relation between P naught and Ni. It is nothing but P naught into Ni into exponential of Ei minus Ef divided by Kt. As this we can mention like Ni e to the power of phi f by phi t. We just multiplied with q on numerator and denominator, and we will get Ni into e to the power of phi f by phi t. In a similar way, I can write N naught, which is nothing but what? The electron concentration, which is minority into or minority concentration in p-type semiconductor. It can be written as Ni. So, into Ni into some exponent. So, whether this exponent will be positive or negative? It will be negative, because Ni is what? Having some value of 10 to the power 10, right. So, intrinsic the minority carrier concentration would be lesser than that, and hence we need to multiply with some negative exponent, which is what? Ef minus Ei by phi t. So, ultimately this will be plus. So, ultimately what we will do? Ni e to the power of minus of phi t by phi f by phi t. This is N naught. Can you relate N naught and Ni from these two equations? So, one equation is N naught is equals to Ni exponential of minus phi f by phi t, and one is P naught equals to Ni exponential of phi f by phi t. With these two equations, I can relate the minority carrier concentration is nothing but you replace Ni from here, right, and put this Ni value here. So, ultimately it will be P naught e to the power of minus of 2 phi f by phi t, where phi f we know is the difference between Ei minus Ef. This is one thing. The another thing we need to know about junction law. What is junction law? In PN junction we generally use, if we have a semiconductor and having two different dopings. For example, here I have a doping N1 and I have a doping N2. Here N stands for electrons, right? And there will be a potential develop in between N1 and N2. Meaning this potential is actually tells us how these dopings are interrelated. For example, if it is positive, it is negative, right? So N1 in terms of N2, again the same thing. If this is positive charge, right, or positive potential, then the electrons will go this side, right? And hence N1 will be more than N2. So ultimately what will happen? Exponential of psi by phi t. If I want to write for N2, what will happen? If I am writing N2, this negative terminal of potential is actually repel the electron that side. So N2 will be written as what? N1 into exponential of minus psi by phi t. This is the junction law which we use in our PN junction theory when we were actually writing the relation between majority and minority carriers across the junction. You know that if it is P, it is N. Majority and minority concentration in P type and N type can be represented as P at P, then N at P. Similarly, this can be written as N at N and P at N. So you can write a junction law to relate these quantities P, P and Pn and all, means how the minority carrier is can be written in terms of majority carrier and vice versa. Here we have seen that Pp is can be written as Pn exponential of, again majority carrier would be higher than the minority carrier, meaning it would be positive. So psi bi divided by phi t, where psi bi is what? Built-in potential. Now with using these two basic understanding of junction law and this carrier concentration, will come back to analyze our surface charge. So again you come back to the basic structure. You have a metal plate here and this is an oxide, this is a semiconductor. You are applying a voltage VGB here, and we are actually analyzing what is the condition when VGB is positive. So we are not talking about the accumulation, we are talking about depletion and inversion. So what will happen if you increase VGB? There will be electrons come into picture, right, near the surface. So again you apply a junction law. From this point to the deep in the bulk, you have potential what? Psi s. And we have also already argued that this surface potential is positive when you are applying a positive voltage from or in between gate to body. If VGB is positive, surface potential will be positive. So N surface, I am writing an equation for the electron concentration which is actually separated by a surface potential. So N surface is equals to N naught. N naught is the concentration at the bulk into the positive, because N surface will be higher, right, because N compared to N naught, compared to the minority carrier at the bulk, N surface will be higher. So it will be positive exponent. Now this N naught, from our basic understanding, this can we remove that? So yes, Ni exponential of psi s minus of phi f divided by phi t. Again, can I replace this Ni by this equation? Because I want to represent what is the N surface. N surface stands for the electron concentration at the surface in terms of what is the doping concentration of the body. So this can be removed as P naught e to the power of psi s minus of 2 phi f by phi t here, right. So using these equations, ultimately you can replace by P naught into this. Now if we consider all the dopants are ionized, it means what? P naught is nothing but what? Na. So N surface is ultimately Na times e to the power of psi s minus 2 phi f by phi t. Let us plot this and again analyze what is actually happening. If we plot the N surface versus psi s, the moment it becomes phi f. So the equation of N surface was Na exponential of psi s minus 2 times of phi f by phi t. I am analyzing this, and this is plotted in a linear scale. So, only the one concentration you can show, that either it is a majority or minority. So, here I am taking one condition, what will happen when psi s is equals to phi f. So, at psi s is equals to phi f. This can be written as n surface is equals to Na into e to the power of minus phi f by phi t. You can go back and check where you can get this type of thing, P naught e to the power of minus phi f by phi t. So, P naught e to the power of minus phi f by phi t will give you what? Here, from here, which is give you what? Ni. So, n surface becomes Ni at psi s is equals to phi f. This is called depletion region. It means what? When you apply the VGB, the uncovered immobile ions will come into picture. There is no mobile carriers will come into picture. That is considered as a depletion condition. So, until surface potential reaches phi f, the n surface, the electron concentration at the surface is equal to, more or less equal to, the intrinsic carrier concentration of the semiconductor. Now, you move further and calculate the n surface for 2 phi f. If you see, n surface is equals to P naught or Na e to the power of psi s minus 2 phi f divided by phi t. At 2 phi f, what will happen? N surface is approximately equals to Na. It means you have applied the gate to body voltage in such a way that the surface potential reaches of value 2 phi f, where phi f is again a known quantity which is given by the difference between the intrinsic level and the Fermi level in a p-type body, right. So, ultimately n surface is exactly equal to what? The doping concentration of the body. That condition is considered to be as inversion. We will explore much more about depletion, inversion and accumulation in subsequent lectures. Let me summarize this lecture, that this says that when you apply a gate to body voltage in the MOS, then different region of operation will come into picture, which is named as flat band condition, accumulation condition, depletion condition and inversion condition. Flat band condition means there is no charge pile up into the semiconductor. Accumulation means that when you are applying a negative voltage into the metal body, then the holes will pile up. We are talking all about p-type body. When you apply a positive voltage in the depletion region, what will happen? Sometimes uncovered ions will come into picture. That uncovered immobile ions causes a depletion region, and hence when if you increase the VGB go beyond 2 phi f, there will be inversion. We have already seen how the charge concentration at the surface dependent on the surface potential. So, n surface can be written as P naught or Na e to the power of psi s minus 2 phi f divided by phi t. So, we will start our next lecture based on this analysis, that the surface potential should increase or be, what will be the value of surface potential and what is in which region of condition our MOS structure operates. So, we will stop here for today. Until then, take care.